Yeah, we are very excited to have Professor Tomás Palacios as our distinguished speaker today. Professor Palacios is a professor in the Department of Electrical Engineering and Computer Science at MIT. He received his PhD from the University of California, Santa Barbara. I guess one could call us like professional siblings. We work under the same PhD advisor. But of course, when I joined, Professor Palacios was already well established at MIT. He received his, he actually did his undergrad degree in telecommunication engineering from the University of Politécnica de Madrid in Spain. His current research focuses on demonstrating new electronic devices and applications for novel semiconductor materials such as graphene and gallium nitride. His work has been recognized with several prestigious awards, including the Presidential Early Career Award for Scientists and Engineers. This is actually the highest honor bestowed by the US government to its scientists and engineers beginning their independent career. He also has been awarded 2012 and 2019 IEEE George Smith Award, and also multiple young faculty awards, including from NSF, ONR, and DARPA, among many others. Professor Palacios is the founder and director of the MIT MTL Center for Graphene Devices and 2D Systems, as well as the chief advisor and co-founder of Cambridge Electronics. He's a fellow of IEEE. Please join me to welcome Professor Palacios, and the podium is yours. Thank you.
Thank you. Thank you so much for the kind introduction. Sorry for the technical glitch. It's a tremendous pleasure to be here today and be able to share with you our vision for the future of electronics. As we all know, electronics has really changed our lives, and it has done it through a few different revolutions. I mean, what I like to call electronics 1.0 was enabled by semiconductor materials, specifically germanium and discrete transistors. Then a new revolution came once that silicon became more mainstream, and that enabled electronics 2.0, the integrated circuit, and the computer revolution that we know of. A few years later, compound semiconductors enabled electronics 3.0, focus on advanced communication, both wirelessly as well as through optical fiber and optical communications. And today, again, materials have introduced a new revolution in electronics, what I like to call electronics 4.0, where thanks to new materials in the gate stack, high-K dielectrics, etc., we are able to have integrated circuits with unprecedented complexity that are enabling the cloud and the internet as we know it. But electronics, rather than staying still, is actually accelerating. And we can see that here on the amount of data that is being generated in the world as a function of year. And it's increasing exponentially. At the same time, the amount of energy used by electronics is also increasing really, really fast. And here we have the energy forecast as a function of a year for basically everything related to electronics, communication, information technology, etc. And the key message is that unless we do something, by year 2030, we are going to have around 21% of all the electricity being generated in the world being used actually by electronics. And this doesn't even account for electric vehicles. So the bottom line is that society is used to the exponential growth of electronics. I would even go one step further. It's not only used to, but desperately needs the exponential growth of electronics to keep improving and keep advancing. But at the same time that we have this need for an exponential improvement in the performance of electronics, today's electronics is facing many different challenges, what I like to call at least five great walls of electronics. The first one, of course, is that the cost of a semiconductor fab keeps increasing exponentially. And these days, you need at least a $10 billion investment to have a single semiconductor fab. Also, the transistors that have driven modern electronics are reaching atomic scale, and it's going to be very, very difficult to continue the scaling, at least at the same pace than before. But even if we are able to make transistors at this nanometer scale, the performance that we get out of these experimental devices lags behind the performance that we would expect from a theoretical point of view. So there is a performance gap between what theory predicts and the experimental data. The fourth big challenge is, of course, the memory bottleneck. It takes a lot more energy to move data around than to actually process that data. And because of that, we need to come up with new architectures. And finally, of course, the fifth great challenge is power dissipation and heat, which ultimately limits all kinds of semiconductor devices. And the energy dissipation, the heat that we are generating in state-of-the-art semiconductor microsystems is extremely, extremely high, and it cannot continue growing. And that limits how we are going to do things in the future. So society desperately needs exponential growth of electronics. At the same time, electronics is facing five really tremendous challenges. I think that's the most exciting opportunity for all of us, electrical engineers, semiconductor device physicists, material scientists, the most exciting opportunity in at least the last 50 years, because we are finally able to change the paradigm of what semiconductor microsystems are about. And this is a once in a generation opportunity to really make a huge impact in the future of society. And that's what I like to call electronics 5.0, the electronics that is going to go after discrete devices, a computer revolution, communication revolution, and the internet and the cloud. But what is this electronics 5.0 about? I think it's all going to be about the edge, what we call edge intelligence. And what we mean by that is that the future, I mean, of course, we are always going to have computers, we are always going to have cell phones, and we are always going to have internet. But the question I'm trying to answer in this seminar today is, what is the next big revolution that is going to add on top of all of that? What is the next $1 trillion opportunity for electronics? And I believe that opportunity is about edge intelligence, is about new microsystems at the edge of the cloud that show a very autonomous behavior in terms of energy, sensing, and data processing. Of course, if we want autonomous behavior of trillions of devices, these devices will have to operate at extremely low power with extremely high efficiency. And there is no silver bullet here. There is no magic material that is going to solve all these challenges at the same time. Because of that, seamless heterogeneous integration of different material systems is going to be absolutely critical. And when we do all of these, I believe that we are also going to be able to enable completely new applications that we cannot even think about today. So that's what I'm going to be talking about today. What are the small steps that my group at MIT is taking to enable this vision for electronics 5.0 or edge intelligence? And something that is going to be absolutely critical for these future electronics is to leverage the unique properties of new families of materials. And in particular, my group focuses on two of those semiconductor materials. First, gallium nitride, or wide bandgap semiconductors in general, including gallium nitride and its alloys with aluminum and indium. This is probably the most important semiconductor the average person has never heard of. It's impacting our lives everywhere, from the solid state LED light bulbs that we have at home, to the displays in our cell phone, to the amplifiers enabling 5G networks and cell phones. But it is just starting to scratch the surface of what this material system can do for us. The second material system we are very excited about is everything related to two-dimensional semiconductors, including graphene, a one atom thick layer of carbon atoms in an hexagonal honeycomb lattice as shown here, as well as other materials like molybdenum disulfide, which is, in this case, 3 atoms in thickness, but also has truly amazing properties. So in today's talk, I'm going to tell you about how we are using these two material families to develop new semiconductor microsystems. And I will divide those into 3 different examples or application areas. I will first tell you about using these new materials on hardware accelerators. This is all about enhancing the performance of silicon chips. How can we take today's silicon chips and make them better? The second big area of research in my group is on ubiquitous electronics. How can we bring electronic microsystems? How can we bring sensing and intelligence to absolutely every object around us, everything in our life? And the third one is a project I'm really excited about because I truly believe it is going to change the way we interact with technology, which is what I call synthetic cells. What would happen to electronics? What is the new form of electronics that we could enable if we are able to make electronic microsystems the size of biological cells? Electronic microsystems so tiny that you can spray them in air and you don't even see them, but they are sensing the environment, talking to each other and communicating with us. So I'll tell you a little bit about each one of these 3 topics over the next few minutes. Let's start with hardware accelerators. And the key advantage that I see for the extreme materials I mentioned before, gallium nitride, as well as two-dimensional materials, is that they can be integrated very easily directly on top of fully fabricated silicon wafers. So we can take a state-of-the-art silicon wafer, sketch here on my back with the devices and the back end of the line, and then in a relatively straightforward manner, especially if we compare that to other materials, we can deposit or synthesize these extreme new materials like 2D materials, like graphene, on the very top of the fully fabricated silicon wafer. And then we pattern and fabricate the devices on these new materials using a thermal budget that doesn't degrade the silicon devices underneath. And in that way, we can bring new functionality to the silicon chip. And we are using this in a wide variety of applications, including in-memory compute, infrared sensing, chemical sensing, quantum computing, as well as power delivery and RF communications. Let me give you a few more specific examples. Let's start with power delivery and RF. I think this is a tremendous opportunity. As I mentioned a few minutes ago, modern microsystems, modern electronics is using a very significant fraction of all the electricity in the world. And by 2030, that number will be at least 20% of all the electricity. And that is not counting on electric vehicles and all these new applications. It turns out that a lot of the electricity that electronics uses is not really being used for doing computation or sensing. A very large fraction of the electricity is actually just wasted during the distribution stage. For example, in a microprocessor, you need to introduce the power at low voltages and high currents because the transistors in silicon can only take a couple of volts of maximum drain voltages. So you introduce it at low voltage, extremely high currents. When you have these very high currents in the range of a few hundred amps going into a tiny microprocessor, any resistance that you have through those very narrow wires that you have in the microprocessor is going to dissipate a very significant amount of power. In fact, around 40 to 50% of all the energy dissipated in a microprocessor is not dissipated by transistors switching on and off and doing computation. No, 40 to 50% of all the energy is dissipated as heat by current flowing through wires. And this is something we can fix. We can fix it if we look at how we do things in a place like the US at the country level with the electric grid. When we generate electricity in the nuclear plants, for example, we generate it at very high voltages to lower the current. We distribute the electricity at high voltages, low currents, and then only locally we down convert those thousands of volts down to the 100 volts that we need at home. And we do that because we don't want to distribute the electricity with very high currents. We need to do the same thing in silicon. And for that, the microsystem we are working on is a microprocessor sketch here, where the energy is introduced at high voltages, around 12 volts, 12 to 20 volts, and low currents. It's distributed at these high voltages to minimize ohmic losses, and then locally is down converted to whatever voltages we need for the logic, the memory, or the RF communication. The question is, how can we make power conversion circuits that are small enough to be integrated with the microprocessor, but at the same time efficient enough to make sure we don't pay a penalty in terms of energy dissipation? For this, we need to use wide bandgap semiconductors like gallium nitride, because this is the only material that allows you to have very high switching frequencies in the order of 100 to 300 megahertz to make sure that the power converters that you need are small enough to not use too much real estate in the microprocessor. So in the future, every microsystem will have a gallium nitride power unit integrated, one or hundreds. And we are prototyping this in many different ways. For example, here we took a silicon microsystem and we flip chip bonded on top a gallium nitride chiplet with 16 different gallium nitride transistors that were doing the power conversion for the system. So we were introducing the voltage around 20 volts and then down converting it to whatever voltages we needed in the actual application. But if we really want to make an impact in power conversion, we need to be able to take advantage of truly CMOS circuitry. Everything we have done so far with gallium nitride has been based on N-type transistors. However, there is a huge body of literature that develops all kinds of circuits by using both P-type and N-type devices. And that is something that gallium nitride has not been able to leverage so far. So in my group, we have been working quite a lot to try to develop a true CMOS technology in gallium nitride. And for that, we started with a conventional gallium nitride enhancement mode, that is positive threshold voltage, N-type transistor, where we have a gallium nitride channel here in blue then an aluminum gallium nitride barrier, and then a p-type layer on top, which is acting like a JFET structure to pinch off the transistor and give us a positive threshold voltage. And of course, we have the source, the drain, and the gate. This is a very well established gallium nitride transistor design. But then, next to it, we fabricated a p-type channel gallium nitride transistor. And for that, we took advantage of the fact that the p-type gate stack in the enhancement mode device is actually depleting the two-dimensional electron gas. So what we did was to keep that in the access regions of our p-type device and use the p-type doping to induce the holes that we needed in our p-type channel transistor. And then we have the source, the drain, and the gate through this UID and intrinsically doped gallium nitride. In that way, we were able to demonstrate the first integrated CMOS circuit in gallium nitride, where we didn't need to use any kind of regrowth technology. We could just use standard epitaxial layers. And this is an example of a p-type gallium nitride transistor that we were able to fabricate with this structure. In this case, we had 40 milliamps per millimeter. Today, we have more than 400 milliamps per millimeter for these p-type devices, which are actually better performing than silicon p-type transistors at the same gate length. So we built a simple gallium nitride CMOS gate driver with a maximum gain around 15. And basically it works as we would expect for a CMOS device. And this is just the very starting point. But what about RF communications? What can we do about RF? How can we improve things significantly with respect to what we have today? And this will be absolutely critical to enable the next generation of cell phone networks, what we call a 6G technology. So one approach is, of course, to bring silicon transistors and gallium nitride transistors close to each other to build integrated heterogeneous systems. And we demonstrated this a few years ago, where we fabricated gallium nitride electronics right next to silicon CMOS electronics. And we demonstrated this on a 6-inch wafer. And the way we did this was by building an SOI wafer, a silicon on insulator wafer. But in this case, the insulator happened to be gallium nitride. And in that way, we have a silicon active layer where we build silicon CMOS devices, then a thin oxide, and then gallium nitride wafer underneath. The big advantage of gallium nitride is that it's very thermally stable and it can survive the standard thermal process of silicon technology. So we could take our SOI, our special SOI wafer, fabricate silicon devices with standard technology, then open windows to expose the gallium nitride underneath, and fabricate the gallium nitride transistors at room temperature. And that's exactly what we have here, the silicon device, the gallium nitride device. And recently, the company Intel has taken a similar approach to demonstrate the integration of gallium nitride devices with silicon on 12-inch wafers, which I think is a truly remarkable result. But then the question is, sure, we can integrate transistors, but what is the very best we can do? What is the ultimate limit for transistor technology in terms of RF amplifiers? So for that, we've looked at different semiconductor materials and the key figures of merit, the key parameters for RF amplifiers. In this case, saturation velocity, breakdown field, and we combine both parameters in what is called the Johnson figure of merit. And of course, gallium nitride is much better than silicon, roughly 10 times better. And diamond is potentially also better than gallium nitride by a factor of 2 or 3. Can we do better than this? Yes. Actually, if we could go from silicon to gallium nitride to diamond to vacuum, vacuum happens to be the best material for electron conduction. That's where electrons reach the highest velocities because there is no scattering. And it also shows extremely high breakdown fields because there is nothing in vacuum. When you combine all that, you get that vacuum devices should be roughly 20 times better than the best you can do with diamond. So let's make a transistor out of vacuum. And this is the diagram of the device we are building, where we have a gallium nitride. Gallium nitride happens to be a very good semiconductor if you want to extract electrons into vacuum, where we have a sharp tip to enhance the extraction of electrons that are traveling all the way from the cathode in the gallium nitride to the anode, which is just a few hundred nanometers apart. And you control the flow of current through a voltage that you apply to the gain on the side. So this is the...
Elahi, can I ask a question?
Sure,
So, Tomás, how is this? This is awfully, I come from a generation where we studied electron tubes.
Excellent.
So how is this different from that? It's very, very similar, right?
It is very similar idea. The main difference is that now we can take advantage of microelectronic fabrication technology and build all this at the nanometer scale. So it's same idea than vacuum tubes, but highly integrated. We can build millions of them on a chip. But
so if one thinks of power, then why not klystrons next?
That comes next. Let's go.
I'm giving out ideas, right?
Absolutely, absolutely. Great point. Absolutely. Yeah. Very good point.
Okay, thank you. Yeah, please carry on. Sorry about that.
No problem. Perfect. So, as I mentioned, gallium nitride happens to be the best material to try to build these field emitters because of two reasons. The atoms in gallium nitride are bonded very strongly to each other. The bond energy is very, very high. So these devices are very robust. On top of that, the electron affinity in a semiconductor is related to how easily you can remove electrons into vacuum. And you need as low electron affinity as you can. Silicon has 4.05 electron volts, silicon carbide 3.6. In gallium nitride, nitrogen phase, you can go all the way to 3.3 electron volts in electron affinity.
What's the electron affinity of gold?
Of gold, I don't remember. Typically metals have lower electron affinity. It's easier to remove carriers, but the challenge there is the gating is a lot more difficult. How to turn off the device is a lot more difficult with metals. But actually, gallium nitride is good, but aluminum nitride is better. By adding aluminum, you can bring the electron affinity down to 0 or even negative values. So I think this is quite promising. And we started to build these devices. This is an ACM image of the gallium nitride tips right there. They are typically in the 20 to 50 nanometer in diameter. And right at the tip, the radius is around 10 nanometers. You need very sharp tips to make sure you can extract the electrons very easily. These round structures are basically the gate electron. And then what we don't show is the top electron that in this case has been removed. So this is how we fabricate it. And the bottom line is that what we have today looks quite promising. This particular device had a maximum current density of around 1 amp per centimeter square. We have devices today based on a second generation structure with around 100 amps per centimeter square, between 10 and 100 amps per centimeter square for a turn-on voltage around 20 volts. So we are still working to lower the turn-on voltage for these devices, but we are getting there. So I am very excited about gallium nitride. I truly believe it has lots of interesting opportunities, but gallium nitride is only the beginning. There are so many other materials with truly unique properties that we can take advantage of. A very good example of that are two-dimensional materials like graphene, like molybdenum disulfide, and like many other thousands of materials, each one of them with their truly unique properties. Out of all of those, my group has been focusing on molybdenum disulfide, a 3-atom thick material, a semiconductor with a band gap around 2.2 to 2.4 electron volts and very good electronic transport. We are very interested in integrating this material on top of a silicon platform. For that, we have developed an 8-inch MOCVD system, a custom-made 8-inch MOCVD system, where we are growing 8-inch molybdenum disulfide layers at very low temperatures, below 300 degrees C. And this is important because it allows us to integrate this semiconductor with pretty much any substrate we want, including fully fabricated silicon wafers. But one of the challenges of any of these two-dimensional materials is the contact resistance. It has traditionally been very difficult to have low contact resistance between a metal and a two-dimensional material. And typical values are many orders of magnitude higher than what you can get with silicon or even gallium nitride. The reason for that is because when you try to contact a 2D material, and this is also true for regular semiconductors, you try to contact a semiconductor with a conventional metal, the states in the semiconductor hybridize with the states in the metal, and that induces mid-level, mid-gap states that are going to pin the Fermi level and are going to increase the contact resistance. And according to our simulations, that has been limiting the contact resistance achievable in these 2D materials. Basically, the mid-level gap states were pinning the Fermi level right at the contact. To fix that, we decided to use a semi-metal rather than a metal, in this case, bismuth. The advantage of a semi-metal like bismuth is that the density of states is going to be very, very low. And the hybridization, the number of hybrid states, the density of hybrid states that you can have between the states in bismuth and the states in molybdenum disulfide is going to be significantly lower than with any other more conventional metal. And by using that, and this is all proven by DFT simulations, etc. But by doing that, we were able to demonstrate a contact resistance to moly disulfide of around 120 ohms a micron, which is very close to the quantum limit for this material. This was the lowest contact resistance demonstrated to 2D materials, as far as I can tell. And with that, we were able to fabricate molybdenum disulfide transistors with on currents in excess of 1 amp per millimeter, or 1100 microamps per micron, which is the highest current density reported in 2D materials. And we think we are just starting to scratch the surface of what we can do with this material that can be deposited on any substrate at temperatures below 300 degrees C, and that because of its extreme thinness, you can have outstanding electrostatic control. So I believe this kind of material system is going to play a very important role in the future of semiconductors. So that was all about my first part, which was hardware accelerators. In the last 10 minutes or so of my talk, I would like to tell you about the two other big application areas that we are excited about. How to bring electronics to everything we have, and what are the opportunities of making electronics so tiny that they become invisible and they are able to float in air and be everywhere. Let's start with ubiquitous electronics. So I think there is a huge opportunity if we are able to change the form factor of electronics and bring electronic sensing and intelligence to everything we have. And for that, we are pursuing different fabrication approaches because, of course, we cannot use conventional semiconductor fabrication to bring electronics to a cup of coffee. One of the approaches we are following is additive manufacturing based on 3D printing. And we modified a 3D printer to be able to print the conventional plastics and ABS material that every 3D printer uses. In addition to those, we wanted to be able to print two-dimensional materials like graphene and molybdenum disulfide. And we did that to be able to print strain sensors based on graphene. For example, the way these sensors work is you print tiny flakes of graphene, and when you apply strain to the structure, the distance between the flakes changes, exponentially changing the amount of current that you can flow through them. So what we did was to use 3D printing to print this quadcopter here. And at the same time that we were printing the legs of the quadcopter, we added strain sensors based on a graphene. And then as we were flying the quadcopter around, we were able to measure real time the strain happening right at that leg in the quadcopter. It's just an example of how we can embed sensing and intelligence in all kinds of objects. But even though 3D printing is very interesting, there are many other applications that are not compatible with 3D printing. For example, textiles and fabrics. So we believe that there is a very interesting opportunity if we are able to bring sensors and semiconductor chips and semiconductor-based electronics to the fibers that make up our fabrics and textiles. And this is just a simple example of that. We took a metallic fiber, a metallic stainless steel thread, and we coated it with a graphitic material shown here. So this is the metallic fibers with the graphitic material. And then we built a pressure sensor out of these fibers by just crossing two of these fibers. And the idea is that you have the metal fiber here coated with a graphitic material, and on top a second fiber. As you apply pressure, you are changing the distance between the two fibers, and you are changing the resistance through the graphitic material in between. And in that way, you can measure the force that you are applying. A very simple sensor. But the power of this is scalability. We have these fibers. Now we start building electronic circuits. And the way we build these electronic circuits is very different from conventional electronics. We just start knitting. And we are able to build very strange looking devices and circuits. Now our devices look like gloves or socks or vests. And each one of these have hundreds of tiny pressure sensors that are monitoring everything we do. So here I have my student, Alisa, testing one of these electronic systems. In this case, the socks she's wearing has a large number of pressure sensors built with the fibers I described before. And as she moves, as she does different activities, the force applied to each sensor is changing. And when you couple that to a machine learning algorithm, we are able to predict exactly what is happening at any given time. This is with socks. We can do something similar with the red vest here. Again, it has embedded in it hundreds of different pressure sensors, which are sending the information to a computer where a machine learning algorithm is able to infer what Alisa is doing at any given time. This is a simple example, but kind of shows that there are lots of interesting things that electronics can do in addition to just microprocessors. But if we want to bring electronics to every object around us, a very important challenge that we need to solve is the challenge of how do we bring energy, power to all these systems. How to power future ubiquitous electronics, because what is very clear is that we are not going to have a power cord connecting these devices to the electric grid. So for the last few years, we've been thinking quite a lot on what are the sources of energy out there. We wanted something that was ubiquitous, that was always on, and that could give us enough power to run these electronic systems. And we found at least part of the answer in the microwave signals that are bringing the internet to our cell phones and laptops. There is a lot of energy and lots of different signals in the 1 gigahertz to 10 gigahertz range of the spectrum for Wi-Fi applications as well as 4G, 5G cell phones. What if we could harvest those tiny amounts of energy and use that to power our sensors and electronics? So I think there is an interesting opportunity there. So we decided to develop a Wi-Fi RF energy harvester. We wanted to be fairly large area because in some applications we need these electronics to span many square meters. We wanted it to also be extremely low cost. We wanted to be able to fabricate it with very crude rudimentary fabrication technologies, but we wanted to have high enough performance to be able to harvest energy in the few gigahertz range. So the way this Wi-Fi energy harvester is organized is we have an antenna, and then we connect the antenna to a rectifier, and this rectifier needs to be able to operate at gigahertz frequencies, but it also needs to be a very low cost rectifier, which rectifies the RF signals, and then we feed those signals to our load. And the way we built that rectifier was by using molybdenum disulfide and using some of the truly unique material science related to this material. For example, one of the properties that I find most interesting is the fact that you can have two different kinds of molybdenum disulfide, either semiconducting or metallic. Same material, just a change in the phase, in the way the atoms are organized, makes the material to be semiconductor or a metal. And you can go from semiconducting to metallic behavior by just exposing the molybdenum disulfide to specific chemicals. And this is very interesting because it allows us to develop truly self-aligned heterojunctions between semiconductors and metals without the need of expensive fabrication processes. You just have the moly disulfide, you deposit a first metal here, a Schottky metal, and then you expose everything else to N-butyl lithium, which transforms the semiconducting moly disulfide into metallic one, on top of which you can make an ohmic contact. In that way, we were able to fabricate Schottky-like rectifiers with extremely low parasitic capacitance, because it's a lateral device, and very low series resistance, because it's truly self-aligned. And everything with basically processing the material on a beaker. And not only that, but we were able to fabricate all of that on a flexible Kapton substrate to be able to demonstrate a Wi-Fi RF energy harvester with around 40% efficiency for input frequencies of 2.4 gigahertz, basically 4G, for power levels in the few hundred microwatts. And it turns out that you can do a lot with just a few microwatts of power, all the way from tiny audio processors to a wide variety of sensors, memory, etc. There has been a lot of work done over the last few years on ultra low power electronics. And I believe that when you combine these kind of energy harvesters with extremely low power electronics, you can build some interesting systems. So those were a few ideas on how to enable ubiquitous electronics. The last few minutes of my talk, I want to focus on a different topic, what I call synthetic cells. What are the opportunities once that you are able to bring electronics to the size of biological cells? Because today's electronics, even though it's amazing and it has changed our lives, is orders of magnitude larger than what nature and biology is able to pack in every single one of our cells. Our average biological cell is 1,000 times smaller than the smallest possible silicon microchip, and it has a little bit of logic, memory, sensing, locomotion, communication, all of that in a really, really tiny volume. So for the last few years, we've had a MURI program funded by the Air Force that was studying what is the ultimate limit of microsystems. And we prototyped a few of these tiny microsystems. And here I have one of them. So this is one of our first generation syn cells or synthetic cells. In this particular case, it has a diameter around 40 microns. So it's a bit larger than a human cell. Human cells are typically in the 5 micron range. So we're still a 10x larger than where we would like to be. But still, in this 40 micron diameter microsystem, we're able to pack a little bit of logic, actuation, energy harvesting, memory, a tiny clock to be able to keep track of time, a little bit of communication, as well as 3 different chemical sensors. And we are starting to ask questions like, what is the minimum performance that we can have in these tiny microsystems and still make them useful? How do we make them flexible and transparent and lightweight? How do we do the energy harvesting? I mean, these are so tiny that you cannot fit an antenna in there. How do you do communications? And given that these tiny systems are going to be very simple, how can we create networks and get them to talk to each other to build more complex systems where there is some cooperation involved? So these are all, I feel, very interesting questions that need to be answered. So we haven't answered all of them. Actually, we are still trying to answer a few, but we do have a few prototypes to play with. All these prototypes are made through heterogeneous integration and packaging of all kinds of materials, including silicon, molybdenum disulfide, gallium nitride, etc., Here I have a vial with a few millions of these syn cells. And a first simple application that we found was to use these tiny syn cells to monitor chemicals in microfluidic channels. So this is a microfluidic channel where we are going to introduce a few of the syn cells. They happen to have magnetic nanoparticles, so they can follow a magnet. So this big circle here is a magnet, and trailing the magnet, you have the syn cells right there, really tiny, going through the microfluidic channel. The diameter of the microfluidic channel is around 200 microns or so. And we expose the syn cells to different chemicals, and then we can find out which are the syn cells that were exposed to putrescine or to just DI water. Again, very simple example, but I feel like it shows the opportunity. But these are so tiny that you can also spray them, and they basically float in the air forever. They're also so tiny that we are embedding them in fibers and starting to build larger systems with them, or use 3D printing, again, to build additive manufacturing. And with this, I would like to conclude by highlighting that we are truly at the most exciting time for electronics in history. And this is thanks to the combination of extreme materials with new devices and all the new applications that they enable. We definitely have unprecedented opportunities for new electronic paradigms. And today I've shared with you 3 of the directions that my group at MIT is working on regarding hardware accelerators, bringing electronics everywhere, ubiquitous electronics, as well as probing the ultimate limit of microsystem performance in synthetic cells. Thank you. Thank you so much for your kind attention. It's absolutely a pleasure to share all of this with you, and happy to take questions. Thank you.
Thanks so much for an amazing talk. Are these synthetic cells that Bill Gates has put in COVID-19 vaccines, or?
Yeah, it's such a problem to try to make sure that the information that gets out there to society is accurate. We are, of course, really far away from these sensors doing anything useful to us. But I do have the dream that one day these sensors will be small enough to be able to be inside our body and help us fight disease. But still many decades away. But I think the key message that I wanted to share in my talk is that microprocessors and computers are really important. Cell phones and the internet are very important, but we should all keep the eyes open for what is next. What is the next big opportunity for electronics and extreme materials?
Yeah, thanks so much. The audience, if you have questions, you can either unmute and ask, or you can put it in the chat and I will read it.
Can I ask you a question?
Sure, go ahead.
Yeah, hi, Tomás. Great to see you. Very nice and amazing work and breadth. So for the MOS2 transistor device you mentioned, can you comment on the stability or reliability of those devices?
Yeah, excellent question. So the molybdenum transistors, as long as you passivate them, they are very stable, but you need to passivate them. You need to deposit something like silicon nitride or aluminum oxide on top. Otherwise, they will react with oxygen and bad things will happen. So either you measure them in vacuum or you passivate them, like we need to passivate every piece of electronics.
So the one you grow, what you mentioned, the 80-inch, are those single crystalline or polycrystalline?
So it's polycrystalline, where we can control the grain size. So depending on the growth conditions, we can go from grain size in the 500 nanometer range to grains in the 50 micron range. Mm. So it depends on the growth conditions.
Okay, thank
Although
you.
to tell you the truth, from an electronics point of view, we have not seen any difference in mobility. The mobility, independently of the grain size, is around 30 centimeters squared per volt per second.
Great. Thank you, Thomas.
Thank you.
Kamal, you have a question? I think we can't hear you, Kamal.
Can you hear me?
Yeah,
Yes.
Oh, okay. Thomas, thank you so much. This was a very inspiring talk, and thank you for accepting our invitation. So my question goes to your nano vacuum tubes that you presented. Can you comment on the noise performance of such devices?
Excellent question. So we haven't studied noise in these devices. I think we are still quite far from being able to have reliable enough devices where we can start to look at those parameters. Right now, so one of the advantages of using a material like gallium nitride or aluminum nitride is that the material is very robust. The atomic bonding energy is very high, so the devices are fairly robust. However, they still degrade quite rapidly, and I think that is also adding to the noise that we may measure here. So to answer your question, we haven't measured noise yet.
Okay, thank you.
Thank you.
On the same topic, may I know if you use a bottom-top approach, like you selectively grow these like nanowires, or is it like by etching?
Great question. Yeah, unfortunately, I didn't have an SEM or TM image of the nanowires, but everything we do is top-down. So we define by lithography, then we etch, and then we have developed different digital etching processes to sharpen the nanowires to the point where at the tip, the radius of curvature is only in the 10 to 15 nanometer range. But then at the base, we want these nanowires to be wider because we want to minimize the access resistance to the tip. So we want wide nanowires at the bottom, very sharp on top.
Thank you. Other questions from audience?
If there is any other question, feel free to send me an email. Always happy to chat about any of these topics and to find collaborations with Michigan.
Sure, thank you. I will then ask just one last question about your work on like integrating GaN with silicon oxide that you showed that. So was that grown on GaN or bonded to GaN? So
this special SOI wafer I was talking about, it was done through wafer bonding. So the way this was done was we had a 6-inch GaN on silicon wafer, silicon 111, and then we did wafer bonding through a silicon dioxide interlayer of an SOI wafer, silicon 100 SOI wafer. We bonded that to the gallium nitride by using silicon dioxide, and then we removed the top silicon carrier wafer to leave behind just the silicon active layer. So it was silicon 100 on top, silicon dioxide bonding layer, and then gallium nitride, and then silicon 111 at the bottom.
Okay, thank you so much. Thank you again for a great talk. And yeah, so I guess you have meetings after. Sopajit has one question. Could you please comment on the output resistance of PGAN HEMS? It seems the output resistance is very low.
Yeah, excellent question. So the output resistance in this particular device was quite high, also because it's a very short channel device. I don't remember what was the gate length in that particular device, but it's probably 100 nanometers or something like that. So short channel effects were quite high, especially because we had a lot of doping in the material. That is a very interesting problem, how to reduce the output resistance in P-type devices. Great point.
Thank you so much. Thank you everyone for attending this great talk. And so I guess you're meeting with the Paula now. Okay, have a good day. Thank you. Bye.
Thank you.